Okay, our aim today is to have a look at scattergraphs and finding the equation of the line of best fit in a scattergraph. So a scattergraph is created from two quantities and we plot them in a scattergraph. What we can look at is how correlated, how connected the quantities are. So if we get a graph that looks like this, where all the points are going in an upwards direction, we say that there's a strong positive correlation. And what we can do there is plot what's called a line of best fit through the centre of the data. So what happens is we get half of the points on one side of the line, half on the other, and the direction of the line follows the direction of the points that have been plotted. The other way that we can see a correlated graph is where the points are going down the way, and this is a strong negative correlation. And again, we can draw a line of best fit in here, but it goes down the way. So again, we have where half the points are on one side of the line, half on the other. So in this case, we've got 2 points on one side, 2 points on the other. And this line happens to go through two of the points. It doesn't necessarily have to, but what you find is that the stronger the relationship between the quantities, the more likely it is, the more tightly packed the points are, so the more likely it is that the line of best fit will go through some of those points. Okay, so in summary, a positive correlation, as one quantity increases, so does the other one, and a negative correlation, as one quantity increases, the other decreases. So that's our second graph. Okay, so let's look at this in terms of a contextual example. What we've got here is data collected on students' weights and heights, and it's plotted into a graph. Okay, so that's done for you, and a line of best fit can be drawn through that. Now that's again done for you, so you can see it here, it's drawn in there. And you can see there again, roughly, this is not an exact thing, but roughly half the points on one side, half on the other. It's quite tightly packed, quite strongly correlated this. So what's happening is that line of best fit is going through two of the points. So what we want to do is actually, for any straight line, we can get an equation for that line, and a line of best fit is no different. We've done this before. We've found equation of straight lines and we've used our y equals mx plus c. So the m and the c are the important bits here that we need to find to be able to get our equation. M is our gradient, so we want to find first of all our gradient for our line of best fit. Now we find the gradient using 2 points on the line. So remember, that's on the line, it's not any of these data points. We can only use the data points if they actually are on the line of best fit, and in this case we do have two of them, so we will use those two, but we can't use sort of these ones here that are either side of the line. They have to be on the line or taking another point entirely, as long as it's on the line, like 20, 60 could be used. But I'm going to use 30, 80 and 50, 130 as my 2 points. It shouldn't matter what 2 points you use, you'll get the same gradient. Remember, the gradient is about the steepness of the line. That's a constant all the way along this line. So underneath my 2 points, just to help me, I've put x1, y1 and x2, y2, and that's to help me with what numbers I put where in my formula for gradient, because remember our gradient formula, y2 minus y1 over x2 minus x1, so 130 minus 80, on the top, 50 minus 30 on the bottom. We work that out as 50 over 20, which simplifies to 5 over 2, and just leave that as 5 over 2. Now you no need to do anything further with that. So the next part is that we want to find the equation of the line of best fit, and it says here in terms of W and H, means weights and heights, but we'll come to that at the end. What we want to think about it is first of all in terms of X and Y, what we're used to, what we're comfortable with, and then we'll deal with the W and the H. Okay, so remember, finding our equation of a line, we need the gradient and a point in the line to help find C. So we've got the gradient, it's 5/2, and use either of these points, or any other point in the line, but let's keep things simple. Use either of these points, and I'm using 30, 80. It's arbitrary. You could use either of them, you'll get the same results. So m is 5/2 and 30, 80 is our x and our y to substitute into our y equals mx+c, so that we can use that information to find c. So 80 for y, 30 for x in place, and then m is 5/2. So the only unknown here is c, and we can rearrange that. 5/2 times 30 is 75. So 80 is equal to 75 plus c, which means c must be 5. So the equation of our line is y equals 5/2x plus 5. Now that's y and x. We need to replace y and x with w and h, because that's what it's been asked for. It's in context of this question here. So w is our x-axis, it's weights for w, and height for h is our y-axis. So we'll replace y with h and x with w, and the numbers are the same. Okay, so it becomes h equals 5/2w plus 5. And that is the equation of our line of best fit in terms of w and h. Now this is very useful because we can use this equation. The reason we've got this is to use it to help estimate data, and that's the next part of this question. So estimate the height of a student who weighs 60 kilograms. So we know that w for weight is 60, so what is h for height? And that's where your equation comes in. So h is equal to 5/2w plus 5. We know that w is 60, so we're going to substitute w into this equation. So h is 5/2 times 60 plus 5. 5/2 times 60 is 150, plus 5 is 155 centimetres. So the estimation of a height of a student who weighs 60 kilograms is 155 centimetres, or 1 metre, 55 centimetres, or 1.55 metres, whichever way you want to write it. It's not asking you specifically there. Okay, so the important points there to know for all of that is to calculate the gradient, we need to use points from the line, not points that are plotted either side of the line. It has to be on the line of best fit. We use that calculated gradient and either of those points that we use for the gradient to find the equation of the line of best fit in terms of y and x, using our equation of our line, our y equals mx+c, as we have done before in the previous unit. And then we replace y and x with the letters given on the graph. So x with whatever it is on the x-axis, y with whatever it is on the y-axis. And then we can use that equation to estimate values. And actually, once you've replaced y and x, it's easier to use the equation because it's in context and you can think about that context a lot more easily. Okay, so that's us run through our line of best fit and our equation of our line of best fit and how we use that.